Welcome to qnawire.
Alright, so we're looking at propylene glycol, and what we need to draw is the most stable Newman projection of propylene glycol, looking down the C1-C2 bond, which I have indicated here with C1 and C2, and I've shown, what the point of view should be with this eyeball, if you will. Right. So one thing that we may notice here is that just sort of a non-standard representation of the molecule in this case, right? And you may also notice that it's kind of confusing because propylene glycol actually has two different stereoisomers, right? So if we draw this more typically, we may say, okay, this is OH. We can add in our implied hydrogens here. Okay. And then we notice that if we put an OH here, well, this has got to either be on a wedge or a dash, right? There are four different constituents on this carbon. That is, we can have this stereocenter, or we can have this stereocenter. So it's just something that's worth pointing out. It won't really have any big effect on the stability of the Newman projection. However, it is the case that there's when you draw that Newman projection, there is one canonical way of drawing it that would be correct that you really can't ascertain from this drawing right here, which is just a little bit strange. So I'm just going to pick this one at random, this particular isomer. It won't have any bearing on the problem in reality, but it will soothe my mind. Okay, so that's C1 and that's C2. Right, so this OH is going to be coming towards us and straight down. Okay, right, we're drawing C1 in the front, and we'll have a hydrogen up to the left and one up to the right, like so. And then our carbon in the back is C2, that's what the circle represents. Okay. And the way we've currently drawn it, we have this ethyl group going straight up. We have OH down to the left. And we have hydrogen down to the right. Now, if we're drawing low energy Newman projections, then we're going to want to stick to staggered projections, which means that we've really only got three different Newman projections to consider, right? We could do the original one, and then we just rotate the rear carbon twice to get the other two projections. So I'm actually just going to copy and paste this twice, and then do the necessary rotations, right? That is to say, I'm moving the groups here. And to make things more clear, I'm actually going to just write ME here for methyl to signify that there's a CH3 group on the end of this here. Okay. So the first rotation will simply be to move everything 120 degrees to the right. So the OH will be on top, the methyl will be down to the right, and the hydrogen will move to being down to the left. And then we do it one more time. So we get OH down to the right, methyl down to the left, and hydrogen on top. Okay, and then at this point, we'll just identify the various interactions that we have, right? And determine which one is better or worse. Okay. So I will use this red to be, okay, that's a gauche interaction between OH and OH. Okay. And I will use blue to be a gauche interaction between methyl and OH. Okay. And we'll see clearly one of these is worse than the other. The one on the right has gauche interactions between OH and methyl. Okay. So then really the question is it better to have OH-OH gauche or OH and methyl gauche? And the answer is that it's best to have and there's something interesting going on here. May not be immediately obvious, at least it wasn't to me. This is the preferred gauche interaction, and the reason for that is that you can actually get hydrogen bonding between these two alcohols. What I mean by that is that, well, actually, I think it'll be easier to show in the sawhorse diagram. So let's consider the sawhorse diagram of this particular molecule, right? So same idea, we just kind of do everything at an angle. Okay. I'm going to do the rear carbon methyl on top, OH down to the left, hydrogen down to the right. But I'm going to draw this a little differently. Okay, here's my OH. Actually, maybe I'll do this a little more. And in the front, right? Hydrogen, hydrogen, and OH. Now the point is that there's a lone pair here, and that we can actually get hydrogen bonding between the hydrogen, oxygen, sort of network here. Hopefully that's sort of apparent. So regardless of how you choose to draw it, I've drawn it in a way that highlights that, but that was just a point. This is how you would typically draw the sawhorse diagram. So this is the lowest energy conformer as a Newman projection, and this is the lowest energy conformer as a sawhorse. Okay, now we're going to look at menthol. I'm just going to draw menthol real quick. All right, and we're going to draw the chair conformer of the most stable conformer of menthol. So remember, we'll get the most stability when groups are equatorial, not axial, right? So let's go ahead and number these 1, 2, 3, 4, 5, 6. I'll number my chair 1, 2, 3, 4, 5, and 6. Okay. And so we want to have methyl on 1, but we'll do equatorial. Better job than that. Okay, equatorial methyl. Jeez. Drawing. Okay, there we go. And then on carbon 3, we'd like to have an OH. Once again, let's do that equatorial. And on carbon 4, we need an isopropyl, and we're free to do that equatorial as well. Okay, so all of our groups are equatorial. That's going to be the most stable conformer. Okay, now we'd like to see, what is cis to each other? So I think it'll help to draw in hydrogens, right, on each of the carbons. Where we have groups. Okay. And quickly we can see, this OH and this methyl are both the lower of the two groups on their respective carbons, which means that those are cis to each other. Okay. Okay, and then we need to draw a top-down wedge-and-dash drawing. So I'm going to draw, I'm going to use the same exact outline here. Right? And then we'll notice, so on carbon 1, this methyl group is the lower of the two, right? So that's simple. I'm going to put Me for methyl. Okay, on carbon 3, OH is the lower of the two. Great. And on carbon 4, isopropyl is the higher of the two. There we go.